point a large telescope at a patch of sky in the constellation Bootes and, for a stretch of space more than 300 million light-years across, you will find almost nothing there. A few dozen faint galaxies drift in a volume that, almost anywhere else in the sky, would hold thousands. This episode follows one through line across the whole history of the universe. The same gravity that gathered matter into galaxies, stars, and eventually us also carved out enormous empty regions between them, patches of near nothing that have been quietly emptying for billions of years. And the same force now accelerating the universe's expansion is stretching those empty regions faster than gravity can ever refill them. We will trace that story from the faint ripples left over from the universe's first fraction of a second, through the vast web of galaxies those ripples became, to a distant future in which almost everything we can see tonight will have receded beyond an horizon of emptiness nothing can outrun. The story of that emptiness in Bootes does not begin with darkness. It begins with light, an afterglow so ancient it fills the entire sky at once, arriving from every direction with almost perfect evenness. Astronomers call it the cosmic microwave background. The relic radiation left over from a moment, about 380,000 years after the universe's birth, when the young cosmos had finally cooled enough for electrons and protons to combine into neutral atoms and let light travel freely for the first time. Almost perfect evenness, but not quite. Mapped in fine detail by orbiting telescopes over the past few decades, that ancient light shows faint variations from patch to patch across the sky, differences of only about 1 part in 100,000. Some regions of the infant universe were very slightly denser than the average, others were very slightly emptier. Neither difference would have been visible to an eye standing in that early fog. They are closer to a whisper than a shout. The whisper was heard almost by accident. In 1965, 2 radio engineers named Arno Penzias and Robert Wilson, testing an antenna meant for satellite communication, kept picking up a faint hiss of microwave static that would not go away no matter which direction they pointed the dish. That static turned out to be the afterglow itself, radiation with a temperature of only about 2.7 degrees above absolute zero, filling every direction in space almost uniformly. It took later missions over the following decades to resolve the faint ripples riding on top of that uniform glow into the detailed maps astronomers study today. That whisper of unevenness is where this entire story starts, because gravity does not ignore even the faintest imbalance. A patch with a little more matter than its surroundings pulls a little harder on everything nearby. A patch with a little less pulls a little weaker. Given enough time, and the universe has had an enormous amount of it, tiny whispers become decisive. Where did the whispers themselves come from? The explanation most cosmologists now treat as their working model traces them back to an extraordinarily brief period, a tiny fraction of a second long, during which the newborn universe expanded at a staggering rate, a phase called inflation. In that model, the ripples began as quantum fluctuations, the ordinary jitter that governs matter and energy at the smallest scales, then got stretched by that rapid expansion until they were large enough to leave a lasting fingerprint on the entire observable universe. It is worth saying plainly that inflation remains a model under active study rather than a settled fact, though the ripple pattern it predicts matches what astronomers actually observe with striking precision. It helps to picture the early universe as something close to a smooth fluid filling all of space almost uniformly, with only the faintest pressure differences moving through it, like sound waves frozen in place at the instant the light we now see was released. Where a compression sat, matter was fractionally denser. Where a rarefaction sat, matter was fractionally sparser. Those frozen sound waves are the density ripples astronomers now read directly off the sky, patch by patch. To make that 1 part in 100,000 difference graspable, imagine a vast, perfectly still lake, its surface everywhere at almost exactly the same level. Now imagine that across that entire lake, some patches sit a hair's width lower than the rest, and some a hair's width higher, spread over a distance too large to walk in a lifetime. That is roughly the scale of imbalance gravity had to work with, everywhere, all at once. None of this, on its own, explains a void hundreds of millions of light-years across, or a web of galaxies stretching across billions more. A ripple of 1 part in 100,000 is not a filament, and it is certainly not an empty gap between filaments. What it is a seed, the smallest possible head start gravity needed to begin sorting the universe into places that would eventually be crowded, and places that would eventually be almost bare. For the first few 100,000 years, radiation pressure, the outward push of light and heat, still fought gravity to a standstill, keeping ordinary matter from collapsing too quickly. But once that fog cleared and light broke free to travel unimpeded, matter was left to answer to gravity alone. From that moment forward, every one of those tiny ripples had roughly 13.8 billion years ahead of it to grow, and that is a very long time for a very small difference to compound. Once light broke free from matter, the sorting could begin in earnest, but most of the heavy lifting in that sorting was not done by anything visible at all. Ordinary matter, the atoms that make up stars, planets, and every one of us, accounts for only a small fraction of everything with mass in the universe. The rest, roughly 5 times as much by mass, is something astronomers call dark matter, material that clumps under gravity exactly like ordinary matter, but does not emit, absorb, or reflect light. It reveals itself only through its gravitational pull, bending the paths of galaxies and light around unseen concentrations of mass. Because dark matter does not interact strongly with light or with ordinary matter, it was free to start clumping under gravity earlier and more efficiently than atoms could, which were still tangled up with radiation pressure until the fog cleared. So the very first structures to form after the ripples were set down were not galaxies, but invisible scaffolding, roughly spherical concentrations of dark matter called halos, growing denser wherever the original ripple had been slightly overdense. Ordinary gas, hydrogen and helium left over from the universe's first few minutes followed that scaffolding once it was free to move. Gas fell into the gravity wells the dark matter halos had already begun to dig, gradually cooling, thickening, and eventually collapsing far enough to ignite the first stars. In every meaningful sense, the visible universe grew up inside a framework that dark matter had already begun assembling first. The process itself follows a principle astronomers sometimes summarize this way. Regions that start out slightly denser than average keep getting relatively denser because their extra gravity draws in still more material from their surroundings, while regions that start out slightly emptier keep getting relatively emptier because they have less gravity to hold on to what little they have. It is not unlike how a slightly larger snowball, once it starts rolling downhill, picks up more snow than a smaller one nearby, purely because it started with a head start. Computer simulations that run this physics forward, starting from the ripple pattern measured in the ancient afterglow light and letting gravity act for billions of simulated years, reproduce something remarkable, not a random scattering of matter, but a connected structure, threads of matter stretching between denser knots, with large, roughly empty regions opening up between the threads. Nobody programmed that shape in by hand. It falls directly out of ordinary gravity acting on tiny original ripples over enormous amounts of time. To put the scale of that head start in human terms, consider that the original density difference between an eventual crowded region and an eventual empty one was, at the start, a difference of roughly 1 part in 100,000, no more dramatic than the difference between a nearly full glass of water and one poured out by a single drop. By the time 13.8 billion years had passed, that single drop of difference had grown into the gulf between a region packed with thousands of galaxies and a region holding almost none. It is worth pausing on just how patient this process is. Unlike a chemical reaction or a nuclear process, which can complete in fractions of a second, gravitational growth on cosmic scales unfolds over hundreds of years continuously, with no dramatic turning point where things suddenly separate into rich and poor regions. The sorting the ripples set in motion in this chapter had been running, quietly, for roughly 1 billion years, before it produced anything anyone would call a galaxy. By the end of that first 1 billion years, though, the shape of the universe's future geography was already largely decided. The regions destined to become dense filaments and clustered walls of galaxies were already visibly denser in the simulations than their surroundings. The regions destined to become the great voids, the enormous, nearly empty bubbles that would eventually include places like the one astronomers would later find in the constellation Bootes, were already visibly emptier. What remained was for that skeleton, invisible dark matter scaffolding wrapped in slowly gathering gas, to take on the recognizable shape that later generations of astronomers would learn to call the cosmic web. Give that gravitational sorting another 1 billion years or so to run, and a genuinely recognizable geometry appears. Matter does not end up scattered randomly, nor does it collapse into isolated, evenly spaced clumps like grains of sand. Instead, it organizes itself into what astronomers now call the cosmic web. Long, thread-like filaments of galaxies and gas, occasionally thickened into broader sheets called walls, all meeting at especially dense knots called nodes, where the richest galaxy clusters eventually form. Threaded between the filaments and walls are enormous, roughly rounded regions where almost nothing formed at all. Those are the voids. A useful, if imperfect, comparison is a sponge, or a dense foam, the kind with thin material stretched between large open bubbles. In that picture, all the galaxies and gas in the universe sit on the thin material, the filaments and walls, while the voids are the bubbles themselves, mostly empty of anything but a faint scattering of stray matter and diffuse gas. Nobody designed the universe to look like a sponge. It is simply the shape gravity produces when it amplifies small, roughly random density ripples for billions of years. This structure did not have to wait for the present day to be confirmed. Beginning in the 1980s and accelerating through large sky surveys that mapped the positions and distances of hundreds of thousands and later millions of galaxies, astronomers were able to build three-dimensional maps of where galaxies actually sit in space. Those maps show exactly the pattern the gravitational simulations predicted: thin, elongated filaments, broader walls, and large gaps between them, matching in overall shape, though not in precise detail, what falls out of the physics. The scale of these structures is genuinely difficult to hold in mind. Individual filaments of galaxies can stretch for several hundred million light-years. For comparison, our own galaxy, the Milky Way, is roughly 100,000 light-years across from edge to edge. A single filament in the cosmic web can therefore be several thousand times longer than our entire galaxy. A single continuous thread of matter, dwarfing the very structures strung along it. The voids between those filaments are comparably vast. A typical void identified in modern galaxy surveys spans anywhere from tens of millions to a few hundred million light-years across, a volume of space so large that a beam of light, travelling at the fastest speed anything can travel, would still take tens or hundreds of millions of years to cross from one side to the other. What makes a void is not that it contains literally nothing. Diffuse gas, dim dwarf galaxies, and the occasional isolated star still drift through even the emptiest regions astronomers have mapped. What defines a void is that its density of matter, on average, sits well below the average density of the universe as a whole, often by a factor of 5 or more, while the filaments and walls surrounding it sit correspondingly above that average. The web, once it takes shape, becomes a kind of permanent geography. Later structures do not form randomly across the universe. They form almost exclusively where the web already provides the gravitational head start of a filament or a wall, and they almost never form deep inside a void, where there is simply not enough surrounding matter to pull anything together. In that sense, the web drawn out over these first couple of billion years does not just describe where matter happens to be. It decides, for essentially the rest of cosmic history, where anything new is even allowed to form. Along the filaments and walls of the newly formed web, gas that had been slowly gathering inside dark matter halos finally grew dense and cool enough, in patches, to collapse under its own weight and ignite the very first stars. This happened within roughly the first few 100 million years after the universe's birth, an era astronomers sometimes call cosmic dawn. Where exactly this happened was never a matter of chance. It happened where the web had already provided enough surrounding matter and gravity to pull gas together in the first place, which meant almost entirely along filaments, and especially at the dense nodes where several filaments meet. As more and more of these early stars ignited across the densest parts of the web, they flooded the surrounding gas with ultraviolet light, energetic enough to strip electrons off the neutral hydrogen atoms that had filled the universe since the release of the ancient afterglow light. This process, called reionization, spread outward from the earliest star-forming regions over hundreds of millions of years, gradually turning a universe filled with a hazy neutral fog into one where light could travel freely across enormous distances, essentially clearing the atmosphere of the cosmos for the first time since its birth. The effect of this on the shape of the universe was to make the already forming web visible, in principle, to any observer with a powerful enough telescope. Galaxies did not appear scattered evenly across the sky. They appeared strung along threads, clustered at intersections and almost entirely absent from the enormous gaps between those threads. exactly mirroring the underlying dark matter structure that had been quietly organizing itself since the very first chapter of this story. Within the voids themselves, during this same era, almost nothing was happening. The gas that did drift through those low-density regions was too thin and too poorly organized by gravity to collapse into stars in any significant numbers. A handful of small, faint galaxies might eventually form on the fringes of a void, pulled together by whatever modest overdensity happened to exist nearby. But the interiors of the largest voids remained, and still remain today, some of the darkest and most starless volumes of space that exist anywhere in the observable universe. It is worth being precise about why this happened, because it is the same mechanism driving everything that follows in this story. Star formation requires gas to be pulled together and compressed, and pulling gas together requires gravity, and gravity requires mass nearby to do the pulling. A region that started out slightly underdense in the very first chapter's ripples simply never had enough surrounding mass to gather gas efficiently, no matter how much cosmic time passed. The emptiness of a void, in other words, is not a separate phenomenon from the richness of a filament. They are the same physical process, gravity concentrating matter where it started out even fractionally denser, viewed from its two opposite outcomes. By the time this era closed, roughly 1 billion years after the universe's birth, the basic geography that continues to shape the sky today was already largely locked in. Regions destined to host billions of stars over the following 12 billion years were already lit with their first generation of galaxies. Regions destined to remain nearly empty for the rest of cosmic history had already fallen too far behind to ever catch up. What had begun as a whisper in the ancient Afterglow light had become, within just a few % of the universe's total age so far, a permanent map of where the lights would turn on and where they would not. And yet the story of the voids in that map was not simply that they were left behind and would stay that way. While the lights across the web kept turning on, generation after generation, something else was happening in the dark gaps between them, something that would take astronomers decades longer to fully appreciate. The voids were not merely staying empty, they were actively becoming emptier still. It would be reasonable to imagine that a void simply stays as empty as it started, a region that missed out on the early advantage the filaments received and has been quietly idle ever since. The real picture, worked out through both theory and detailed computer simulations over the past few decades, is more active than that. Voids do not just fail to fill up. Over billions of years, whatever matter they do contain tends to drain outward, toward the denser walls and filaments that surround them, leaving the interior of a mature void emptier, relative to the average density of the universe, than it was when it first formed. The mechanism is straightforward once the geography is in mind. A void sits surrounded on essentially every side by regions of higher than average density, the filaments and walls of the web. Gravity from those denser surroundings pulls outward on anything sitting near the edge of the void, and with comparatively little mass inside the void itself to pull back, that outward pull wins. Matter near a void's edge is gradually drawn toward the wall it borders, in much the same way that people standing near the edge of a nearly empty room will tend to drift toward whichever adjoining room is louder and more crowded, simply because there is more happening, and more pulling their attention on that side. This has a second, less intuitive consequence. Because a void contains less matter than average, its own gravity is weaker than average at slowing down the overall expansion of space within it. The universe as a whole is expanding, and ordinarily gravity acts to slow that expansion down locally, more strongly wherever there is more mass. Inside a void, with comparatively little mass to do that slowing, the local expansion rate runs very slightly faster than the universal average. In effect, a void does not just lose matter outward toward its walls. The space inside it also stretches a touch faster than the space around denser regions, compounding the emptying from the inside as well as the outside. Neither effect is dramatic on any human timescale. The extra expansion rate inside a typical void differs from the cosmic average by only a small fraction, and the outward drift of matter toward a void's edges unfolds over many hundreds of millions of years. But cosmic history has had ample time for small, patient effects to add up, and by the present day the emptiest regions of the universe are measurably emptier, relative to the cosmic average, than they were when the cosmic web first took shape. A useful way to picture the overall effect is a slow, continuous thinning, like a sparse crowd in an open field gradually drifting toward the noise and lights of a nearby street fair. not because anyone told them to, but because there was simply more to be drawn toward on that side. Nobody in the field decided to leave all at once. Over hours, the field simply empties further than it started, while the street fair grows more crowded still. This slow draining explains something that might otherwise seem strange. Why the voids astronomers eventually found and measured in detail turned out to be even emptier, relative to their surroundings, than the simplest expectation from the original density ripples alone would suggest. The ripple that seeded a given void was only ever a small underdensity to begin with, perhaps a modest fraction below the cosmic average. Billions of years of this outward drainage, compounded with slightly faster local expansion, is what turned that modest early underdensity into the profound emptiness astronomers now find when they actually look. This process had been quietly running for most of cosmic history, largely unnoticed, long before anyone on Earth had a telescope capable of detecting it directly. It would take until the second half of the 20th century for astronomers to build instruments capable of mapping galaxy positions across large enough volumes of the sky to notice the emptiness at all. And when they finally did, the ind would be even larger and even barer than most had expected. Before turning to the most famous individual void astronomers have found, it is worth pausing on our own address within this emptying web. The Milky Way sits within a modest collection of a few dozen galaxies called the local group, itself part of a broader, flattened structure of galaxies called the local sheet. Bordering that sheet in one direction lies a genuinely large gap known simply as the local void, a region tens of millions of light-years across containing far fewer galaxies than the surrounding volume, close enough that its effects on the motion of nearby galaxies can actually be measured. A more provocative, and considerably more debated, idea goes further. Around 2013, 3 astronomers, Ryan Keenan, Amy Barger and Lennox Cowie, published an analysis suggesting that the Milky Way might sit not just near a modest local gap, but somewhere close to the middle of a far larger underdense region, since nicknamed the KBC void after their initials, potentially around 2 billion light-years across. For comparison, the entire observable universe, the volume from which light has had time to reach us since its birth, is roughly 93 billion light-years across. A void of that scale would still be a small fraction of the observable universe as a whole, but considerably larger than most voids astronomers had previously catalogued, and unusually large for one that happened to contain our own galaxy near its centre. Why would this matter beyond simple curiosity about our cosmic neighbourhood? Because measuring how fast the universe is expanding, a number called the Hubble constant gives slightly different answers depending on the method used. Measurements based on relatively nearby objects tend to come out a little higher than measurements based on the ancient afterglow light from the early universe. This mismatch, often called the Hubble tension, remains one of the more actively debated open questions in cosmology. Some astronomers have proposed that if the Milky Way really does sit inside an unusually large underdense region, the weaker than average gravity there could cause nearby galaxies to be pulled outward a little faster than the true cosmic average, artificially inflating local measurements of the expansion rate, and helping explain at least part of the mismatch. This remains genuinely unsettled. Other studies, using different galaxy surveys and different methods, have found less evidence for an underdensity as large or as centered on us as the original proposal suggested, and the Hubble tension itself may well have other causes entirely, some having nothing to do with local structure at all. It would be inaccurate to present the KBC void as a confirmed explanation for anything. It is best understood as one live hypothesis among several, illustrating just how directly the emptiness of the local universe can, in principle, tangle itself into even the most fundamental numbers cosmologists try to measure. What is not in serious dispute is that our part of the universe is, at the very least, somewhat less dense than the cosmic average, sitting on the edge of the local sheet, bordering the local void, within a broader region that at least some analyses suggest is unusually empty on a larger scale still. Whether we happen to live near the centre of an exceptionally rare underdensity, or simply in an ordinary, modestly empty patch of a universe full of such patches, remains an open question that better data from ongoing and future galaxy surveys may eventually settle. Whether or not our own neighbourhood turns out to be exceptional, the largest individual void ever identified with confidence was found decades before this local debate began, and in a very different way. Not through a subtle statistical argument about the expansion rate, but through the far more direct method of simply counting galaxies and finding, in one particular patch of sky, that there were almost none there at all. In 1981, a team of astronomers led by Robert Kirshner was carrying out a survey designed to measure the distances to a modest sample of galaxies in the direction of the constellation Bootes, hoping to test how galaxies were distributed at that particular patch of sky. What they found instead was startling enough to reshape how astronomers thought about cosmic structure. Within a volume of space roughly 330 million light-years across, they counted only a small handful of galaxies, where a region of that size elsewhere in the sky would ordinarily contain many thousands. The astronomers involved reportedly joked at the time that if the Milky Way had happened to sit inside that void rather than where it actually does, humanity might not have discovered that other galaxies existed at all until telescopes had advanced considerably further than they had by the 1920s, since even the nearest large galaxy cluster beyond the void's edge would have appeared as an exceptionally faint and distant smudge rather than the rich, easily studied structures. Nearby galaxy clusters actually appear as from Earth's own vantage point. The Bootes void, as it came to be known, is not literally empty. Later, more sensitive surveys found a modest population of additional faint galaxies scattered through its interior that the original 1981 survey had simply been too limited to detect, bringing the total closer to a few dozen, rather than the handful first reported. But even with that correction, the region remains dramatically underpopulated compared to its surroundings, and it served for years afterward as the textbook example that finally convinced a skeptical astronomical community that voids of this scale were a genuine and common feature of the universe's structure, not a fluke of one unusual survey. What made the discovery so influential was timing as much as scale. Through the 1970s, most cosmologists had assumed that galaxies were distributed through space in a roughly smooth, only mildly clumpy way. The Bootes void, discovered within a few years of the first large-scale galaxy redshift surveys that could actually map three-dimensional positions rather than just positions on the sky, was one of the clearest early pieces of evidence that the universe's true structure looked far more dramatic than that. Not a smooth haze of galaxies, but a web of dense filaments wrapped around genuinely enormous empty gaps, exactly the picture later confirmed by every major galaxy survey since. For scale, 330 million light-years is roughly 3,300 times the diameter of the Milky Way. Laid end to end, that is a distance a beam of light, the fastest anything can travel, would take 330 million years to cross, longer than the time separating the first land animals on Earth from the dinosaurs that would eventually follow them. And within that entire volume, decades of increasingly sensitive surveys have found only a scattering of isolated, faint galaxies, drifting largely alone through a darkness that dwarfs anything a human mind naturally scales itself against. The Bootes void was, in a real sense, the moment voids stopped being a theoretical curiosity implied by simulations and became an observed, measured, undeniable feature of the actual universe. And its discovery raised an obvious next question. One astronomers spent much of the following decades answering, what, if anything, lived inside places like it, and were the handful of galaxies that did exist there ordinary, or were they, in some measurable way, different from galaxies that had grown up in busier neighborhoods? The scattered galaxies that do exist inside large voids turned out, on closer study, to be genuinely different from galaxies that grew up in the crowded filaments and walls of the cosmic web, and the reasons for that difference traced directly back to the same isolation that makes a void in the first place. Void galaxies tend to be smaller than average, richer in raw hydrogen gas, and bluer in color, a color that in astronomy generally signals young, hot, recently formed stars rather than an older, redder population that stopped forming new stars long ago. In a dense galaxy cluster, individual galaxies regularly interact with their neighbors. They pass close enough to distort each other's shape with gravity, occasionally collide and merge outright, or plow through a hot, diffuse gas that fills the space between cluster galaxies, a process called ram pressure stripping that can physically scour a galaxy's own gas supply away, cutting off the raw material it needs to keep forming new stars. Over billions of years, this crowded, collision-prone environment tends to redden a cluster's galaxies, exhaust their gas, and settle them into a more passive aging population. A galaxy drifting through the middle of a large void experiences almost none of this. With few or no close neighbours to interact with, it keeps hold of its own gas supply far longer, continues forming new stars at a comparatively steady rate, and ages in relative isolation, largely undisturbed by the gravitational battering that shapes galaxies in busier parts of the web. In an important sense, a void galaxy is closer to a preserved snapshot of what an isolated galaxy left mostly to itself looks like after billions of years, rather than a galaxy that has been repeatedly reshaped by its surroundings. This makes void galaxies genuinely useful to astronomers, beyond simple curiosity about their appearance. Because they have been so lightly disturbed by their environment, they offer something close to a natural control group, letting astronomers separate what a galaxy's own internal physics does to it over time from what a crowded environment does to it. Comparing a void galaxy's properties to an otherwise similar galaxy that grew up inside a dense cluster helps isolate exactly which of a galaxy's features come from nature, so to speak, and which come from neighbourhood. It is worth being precise that void galaxies are not entirely cut off from the rest of the universe. Many still sit near the fringes of their void, close enough to a bordering filament or wall to have formed with at least some initial gravitational assistance, and some studies suggest even isolated void galaxies show subtle effects in their rotation and structure that hint at the very slightly faster local expansion rate described earlier, draining matter away at the edges. But compared to almost anything living inside a filament, wall or cluster, a void galaxy leads a remarkably quiet, undisturbed existence. That quiet existence, multiplied across every void astronomers have catalogued, adds up to a genuinely large population. Current estimates suggest voids, despite their emptiness, still contain a meaningful fraction, somewhere in the range of 10 to 20%, of all the galaxies in the observable universe, simply spread across such enormous volumes that any individual patch of a void appears nearly empty, even though the void as a whole is not literally devoid of galaxies at all. While these scattered, undisturbed galaxies drifted largely unbothered through their empty neighbourhoods, a much larger discovery, unfolding at the very end of the 20th century, was about to change how astronomers understood the fate of every void in the universe, not just their present contents. In 1998, two independent teams of astronomers studying a particular kind of exploding star called a Type 1a supernova arrived at the same startling conclusion. These particular explosions, the violent detonation of a dense stellar remnant called a white dwarf, after it accumulates too much mass to remain stable, reach a strikingly consistent peak brightness, which lets astronomers use them as reliable distance markers. Measure how faint one of these explosions appears from Earth, and you can work out with reasonable confidence how far away it actually is. When the two teams compared those measured distances to the redshift of the galaxies hosting the supernovae, a number that reveals how much the universe has expanded since the light left its source, they found something nobody had expected. Distant supernovae appeared fainter, and therefore farther away than they should have been if the universe's expansion were simply slowing down under its own gravity, as most cosmologists had assumed it must be. The only way to explain the mismatch was that the universe's expansion has been speeding up, not slowing down for roughly the past 5 to 6 billion years. In 2011, three astronomers central to that discovery, Saul Perlmutter, Brian Schmidt, and Adam Rias, were awarded the Nobel Prize in Physics for the finding. Whatever is causing that acceleration, astronomers have given it a placeholder name, dark energy. It is important to be honest about how little is actually known about what dark energy fundamentally is. The simplest and most widely used model treats it as a property built into space itself, a kind of constant energy density that does not dilute as the universe expands, unlike ordinary matter, which spreads out and thins as space grows. That model fits the available data well, but it does not explain, at a deeper physical level, why space should carry that energy in the first place, and alternative explanations remain under active study. Whatever dark energy turns out to be, its effect on the voids traced through this episode is disproportionate, and the reason comes down to a distinction that matters enormously here: bound structures versus unbound space. A galaxy, held together by its own internal gravity, does not expand along with the universe around it, in the same way that a solar system's planets do not gradually drift farther from their star, just because the space between distant galaxies is stretching. Gravity within a bound structure is simply strong enough to resist the overall cosmic stretching entirely. A void, by definition, contains far too little matter to bind itself together in that way. Space inside a void is freer to simply follow the universe's overall expansion, unresisted by any significant internal gravity. As that overall expansion accelerates, the interiors of voids stretch correspondingly faster, while the galaxies, clusters and filaments around their edges hold their shape almost entirely unchanged. The imagery cosmologists sometimes reach for is a loaf of raisin bread rising in an oven. The raisins, held together by their own structure, barely change size, while the dough between them, unbound and free to expand, stretches steadily larger the longer the loaf bakes. The practical result is that dark energy, whatever its ultimate nature, acts almost like a magnifying glass specifically for the emptiest parts of the universe. Every mechanism traced through this episode so far, the original density ripples, gravity's long sorting, the slow drainage of matter out toward denser walls, was already making voids relatively emptier over cosmic time. Dark energy adds a second, independent process on top of all of that, one that does not touch the dense filaments and clusters nearly as strongly, but that stretches the empty spaces between them ever faster, with no sign, based on current evidence, of that acceleration slowing back down. Because voids respond to dark energies stretching so much more purely than any other structure in the universe, tangled as little as anything can be with the complicating effects of their own gravity, they turned out, somewhat unexpectedly, to be one of the single best places astronomers could actually go looking to measure what dark energy is doing in detail. Once astronomers recognized that voids respond to dark energies stretching in an unusually clean, unobstructed way, the natural next step was to stop treating individual voids as curiosities and start treating the entire population of voids across the sky as a measurement tool in its own right. Large modern galaxy surveys, capable of mapping the three-dimensional positions of millions of galaxies across huge stretches of the observable universe, now let astronomers identify and catalogue thousands of individual voids rather than the handful that had been found by hand in earlier decades. With a large enough catalogue in hand, astronomers can ask statistical questions that a single void could never answer on its own. How many voids of a given size exist at a given distance, and therefore at a given point in cosmic history, since looking farther away always means looking further back in time? How does that number change as you look closer to the present day? How round or irregular are typical void shapes, and does that shape distribution shift over cosmic time in a way that matches the predictions of a universe dominated by dark energy behaving the way the simplest models expect? Each of these questions provides a check on cosmology's overall picture that is at least partly independent of the more familiar measurements astronomers already use, such as the clustering pattern of galaxies themselves or the detailed structure of the ancient afterglow light. Because voids are shaped by the tug-of-war between gravity trying to hold structure together and dark energy trying to stretch it apart, precisely tracking how void sizes and shapes evolve over cosmic history offers a genuinely separate line of evidence for how strong that tug-of-war has actually been at different points in the universe's past. This approach has already turned up subtle, useful results. The overall statistics of large void catalogues, compiled from major surveys over roughly the past 2 decades, are broadly consistent with the standard picture of a universe whose expansion has been accelerating for the past 5 to 6 billion years, adding further independent support to a conclusion originally reached through the very different method of studying distant supernovae. Some studies using void statistics have also placed useful limits on alternative theories that try to explain cosmic acceleration through a modification to gravity itself, rather than through a separate dark energy component, since such modified gravity models tend to predict subtly different void shapes and abundances than the standard picture does. The practical challenge in this kind of work is considerable. Identifying a void reliably in a real galaxy survey, distinguishing a genuine low-density region from an area that simply has fewer galaxies bright enough for a given telescope to detect, requires careful statistical methods and enormous amounts of data. It is a much harder problem than it sounds, and the field has spent much of the past 2 decades refining exactly how to define and measure a void consistently enough for the comparisons across different surveys to actually mean something. What makes this line of research valuable is precisely its independence from other methods. Cosmology, as a science, gains confidence not from any single measurement, but from multiple, genuinely different methods converging on the same answer. Supernovae point one way. The ancient afterglow light points another. The large-scale clustering of galaxies points a third. and now, increasingly, the sizes, shapes, and abundances of the emptiest regions of the universe, the voids this whole episode has been following, provide yet another independent line of evidence, converging, so far, on the same broad picture, a universe whose expansion has been accelerating for billions of years, and whose emptiest places are stretching fastest of all. Voids were not just passively expanding under all this either. As the surveys underlying this research grew more detailed, astronomers noticed something else. The galaxies bordering these voids were not simply drifting outward under the void's expansion in a perfectly smooth, symmetric way. Some were moving in directions that suggested something closer to an actual push, and the source of that push led directly back to the emptiness itself. Galaxies do not simply sit still while the universe expands around them. Beyond the overall stretching of space that carries every distant galaxy slowly farther from every other, galaxies also have what astronomers call peculiar velocities, motion caused by the gravitational tug of nearby structure layered on top of the universal expansion. The Milky Way itself, along with the rest of the local group, is moving at roughly 600 kilometers per second relative to the average motion of matter across the observable universe, a speed fast enough to cross the entire diameter of Earth in under a minute. For decades, astronomers explained most of that motion as a pull toward a massive concentration of galaxies in the direction of the constellations Norma and Centaurus, an especially dense region nicknamed the Great Attractor, whose gravity draws in galaxies across a substantial stretch of our local corner of the universe. In 2014, a more complete mapping effort identified the full extent of the gravitational basin the Milky Way actually belongs to, a vast supercluster of roughly 100,000 galaxies spanning about 500 million light-years, named Laniakea, a word drawn from Hawaiian meaning immense heaven, with the Great Attractor sitting near its gravitational center. More recently, a 2017 analysis proposed that at least part of the local group's motion might not be a pull toward density at all, but a push away from emptiness. Mapping the distribution of galaxies on the far side of the Milky Way's motion from the Great Attractor, the researchers identified a large, sparsely populated region, since named the dipole repeller, whose comparative lack of gravity, relative to its denser surroundings, would effectively cause nearby galaxies to be relatively pushed toward the busier regions on the opposite side, simply because there is less pulling them back on the empty side. This is a genuinely subtle physical point worth stating carefully. Nothing is being repelled by any actual repulsive force. What is happening is that an underdense region exerts less gravitational pull than an overdense region of comparable distance would, and in a universe where galaxies are being pulled from multiple directions at once, a region with unusually weak pull on one side produces a net effect indistinguishable, in practice, from being pushed away from that side. A useful comparison is standing at the boundary between two crowded rooms and one nearly empty one. Even if nobody in either crowded room is deliberately pulling you toward them, you would still find yourself carried, on balance, away from the empty room and toward wherever there is more to be drawn toward. The dipole repeller remains, like the KBC void discussed earlier in this episode, a genuinely debated idea rather than settled consensus. Some analyses find it accounts for a meaningful fraction of the local group's total motion. Others find the effect harder to disentangle cleanly from the pull of known overdense structures like Laniakea and the Great Attractor. What both hypotheses share, whether or not either one turns out to be exactly right in its current form, is the same underlying lesson this whole episode has been building toward. The voids are not simply passive backdrops to the more dramatic story of galaxies and clusters. Their absence of matter is itself a gravitational actor, shaping the motion of everything nearby just as surely as any dense structure does, only in the opposite direction. All of this motion, pulled or pushed, unfolded within a universe whose densest structures were, by this point in cosmic history, approaching something close to their final form, even as the emptiest structures around them were only just beginning the phase of their story that would come to dominate everything that followed. For roughly the first 9 billion years of the universe's history, gravity had the upper hand. Matter, both ordinary and dark, was dense enough overall that its combined pull dominated the universe's dynamics, steadily slowing the rate of cosmic expansion and continuing to build ever larger bound structures, up to genuinely massive galaxy clusters bound together by their own gravity across millions of light years. somewhere around 5 to 6 billion years ago. As the universe continued expanding and ordinary and dark matter thinned out correspondingly, the balance tipped. Dark energy, whose energy density does not dilute as space expands in the simplest and most widely supported model, came to dominate the universe's overall dynamics for the first time, and the deceleration of cosmic expansion that gravity had maintained for billions of years reversed into the acceleration astronomers detected through the supernova observations described earlier. That tipping point matters enormously for the fate of large-scale structure, because it marks roughly the beginning of the end for building genuinely new large-bound structures. Before dark energy took over, gravity had enough relative strength across large volumes of space to keep pulling together matter separated by hundreds of millions of light-years, assembling superclusters like our own Laniakea. After dark energy took over, the accelerating stretching of space between distant regions increasingly outpaces gravity's ability to draw them together in the first place, making it progressively harder, and eventually essentially impossible, for entirely new structures on that scale to ever form. This does not mean structure formation has stopped everywhere, immediately. Within regions already gravitationally bound, galaxies continue merging, stars continue forming, and even entire galaxy clusters can continue growing by pulling in already nearby material that has not yet had time to be carried out of reach. Our own Milky Way, for instance, is still on a slow collision course with the neighbouring Andromeda galaxy, expected to merge with it over the next several billion years, entirely unaffected by the accelerating expansion happening on much larger scales beyond the local group's own gravity. What has effectively ended, or is in the process of ending, is the formation of anything genuinely new at the very largest scales, structures the size of Laniakea or larger, built from regions of the universe not already gravitationally bound to each other. Some cosmologists studying this transition describe the present cosmic era as sitting close to, or perhaps just past, the peak of large-scale structure formation in the universe's entire history, a genuinely striking thing to be able to say about the particular moment in cosmic time we happen to be observing it from. It is worth placing this in a wider perspective before treating it as some sort of ending. 13.8 billion years sounds enormous by any everyday measure, but stars like the Sun can continue shining for billions of years yet, and the smallest, most efficient stars in the universe are expected to keep burning for trillions of years beyond that. In cosmic terms, we are observing this structural turning point extremely early, closer to the beginning of the universe's total story than to any meaningful middle or end, even though the largest bound structures may already be nearly as large as they will ever get. From this point forward, the two halves of this episode's story increasingly diverge. The filaments, walls and clusters that make up the crowded side of the cosmic web largely stop growing at the very largest scales, settling into structures that will persist, essentially unchanged in their own internal gravity, for a very long time to come. The voids between them, however, driven by the same dark energy that just ended large-scale structure formation, do not stop growing at all. If anything, their expansion is only getting started. If dark energy continues behaving the way current observations suggest, the accelerating expansion of the voids this episode has been tracing carries a genuinely striking long-term consequence. One models predict will unfold gradually over the next tens to hundreds of billions of years. Any galaxy not gravitationally bound to our own local group, meaning any galaxy far enough away that its own gravity and ours are too weak to hold it in place against the accelerating expansion of space between us, will eventually recede fast enough that the space between us stretches faster than light can cross it. This is worth explaining carefully, because it can sound as though it breaks a fundamental rule of physics. Nothing is actually travelling through space faster than light. What is happening is that space itself, the distance between 2 points, is stretching, and there is no upper limit on how fast that stretching can accumulate across a sufficiently large distance, even while nothing local is moving faster than light through the space immediately around it. Once the accumulated stretching between two galaxies grows fast enough, light leaving one can never again cross the ever-widening gap to reach the other, no matter how long it travels. The practical consequence is a boundary astronomers call a cosmic horizon, a maximum distance beyond which, given enough time, we will never again receive light from anything, and beyond which nothing we send could ever arrive either. As the universe's accelerating expansion continues, that horizon does not grow to include more of the universe over time. Instead, it functions almost like a slowly closing curtain. Galaxies currently visible near its edge will, one by one, cross beyond it, their light growing fainter and shifting further toward the red end of the spectrum as the space it has travelled through stretches, until eventually it grows too faint and too stretched to detect at all. What remains visible on the far side of that gradual closing is whatever happens to be gravitationally bound closely enough to resist the stretching entirely. For us, that means the local group and whatever the Milky Way and Andromeda eventually merge into after their expected collision several billion years from now, along with perhaps a small handful of the very nearest bound structures, becoming in effect an island, a single, permanently self-contained pocket of galaxies, surrounded on every side by space, that has stretched every other galaxy's light beyond any hope of ever reaching it again. This isolation would not happen everywhere at once, nor would it happen quickly by any human measure. It is a genuinely gradual process, unfolding over the deep future this episode has now moved into, tens of billions of years and beyond, each individual distant galaxy crossing the horizon on its own schedule, determined by exactly how far away it started and exactly how the acceleration continues to play out. It is also worth repeating that this entire picture rests on an extrapolation, on the assumption that dark energy, whatever it fundamentally is, keeps behaving the way current data suggests indefinitely into a future far longer than the entire history of the universe observed so far. With that hedge firmly in place, the picture current evidence points toward is nonetheless a striking one. What began in the very first chapter of this episode as an almost imperceptible whisper of unevenness in the universe's oldest light and grew, over billions of years, into a rich connected web of galaxies visible across enormous stretches of the observable universe, is now, according to the same physics that built it, slowly and irreversibly unbuilding itself, one galaxy's light at a time, back toward isolated islands surrounded by an emptiness with no edges left to drain toward. It helps to picture this deep future concretely, from the vantage point of whatever bound structure survives, rather than as an abstract description of expanding space. Current extrapolations suggest that within roughly 100 billion years, an amount of time roughly 7 times the current age of the universe, an observer within the merged remnant of the Milky Way and Andromeda, would find that essentially every galaxy not already part of that merger has crossed beyond the cosmic horizon described in the previous chapter, its light having faded and reddened past any possibility of detection. This does not mean those other galaxies stop existing. Matter does not vanish, and nothing about this process destroys anything physically. It means those galaxies become permanently causally disconnected from us. Nothing that happens there can ever again influence anything here, and nothing that happens here can ever again influence anything there, because the space between us has stretched too fast for any signal, light included, to ever cross it. From our side of that boundary, it would look, for all practical purposes, exactly as though those galaxies had ceased to exist, even though, from their own perspective, they would continue on entirely undisturbed, observing their own version of the same isolating process happening to us. An observer living inside that surviving island, tens of billions of years from now, looking out at the night sky, would see something genuinely different from anything visible from Earth today. No other galaxies at all, no distant clusters, no filaments stretching across the darkness, only the stars of their own merged home galaxy, themselves slowly burning out and dimming over the following trillions of years, as the universe's stock of gas available to form new stars is gradually used up. The sky such an observer would look up at would be, in every meaningful sense, what the interior of a void looks like today, only extended to cover essentially the entire universe, rather than confined to isolated pockets between filaments. This is the deep, hedge-heavy conclusion this entire episode has been building toward. The emptiness astronomers first noticed in patches, like the region in Boots, or the debated underdensity that may or may not surround our own galaxy, is not a strange local anomaly confined to a few unlucky corners of the universe. According to current evidence and current models, it is a preview, the specific fate that accelerating expansion appears to have in store for essentially everything, given enough time, with only the small handful of already gravitationally bound structures scattered throughout the universe surviving as isolated exceptions. It is worth restating one final time exactly how much this deep future picture depends on assumptions that current evidence cannot fully confirm. Dark energy's fundamental nature remains genuinely unknown, Whether it continues acting exactly the way the simplest models predict, indefinitely, over timescales vastly longer than anything humanity has directly observed, is an extrapolation, not a measurement. It is entirely possible that some property of dark energy not yet detected could alter this picture meaningfully over such enormous stretches of time. The confident parts of this story are the parts already measured: the density ripples, the cosmic web, the discovered voids, the accelerating expansion itself. The deep future built from projecting that acceleration forward for 100 billion years and beyond is the most speculative extension of an otherwise well-supported story, and it should be held with appropriately loose hands. With that important hedge in place, it is time to step back from the deep future entirely and return to what is solid, what this whole story, from the faintest ripple in the universe's oldest light to the emptiest void ever catalogued, actually tells us about the universe we happen to be living in right now. It is worth returning one last time to that patch of sky in Boots, 330 million light-years of nearly empty space, discovered almost by accident in 1981 by a survey that had set out to measure something else entirely. Calling a region like that a giant empty void eating the universe makes for a dramatic description, and in a loose sense it is not wrong. Voids genuinely are growing, and they genuinely are consuming, in the sense of overtaking, an ever larger share of the universe's total volume as cosmic time passes. But the word eating suggests something hungry, something acting with intent, devouring structure that would otherwise have survived. Nothing in the physics traced through this episode supports that picture. Every mechanism this episode has followed traces back to the same single cause: tiny density ripples, differences of only about 1 part in 100,000, present in the universe's oldest light. Gravity did not create two separate stories, one building galaxies and another separately destroying empty space. It ran one story, amplifying wherever there was slightly more matter, and by the same exact process, thinning wherever there was slightly less. The rich cosmic web of filaments, walls, and galaxy clusters, and the vast empty voids between them, are two faces of one physical process, not a battle between construction and destruction. Dark energy, whatever it ultimately turns out to be at a deeper level, did not introduce a new destructive force into that story either. It simply let an old asymmetry run further and faster than gravity alone ever could. Bound structures, held together by their own internal gravity, were essentially unaffected. Unbound space, already thinner than average inside every void, was free to stretch, and stretch it did, accelerating over the past 5 to 6 billion years, in a way that current evidence shows no sign of reversing. What this leaves us with is a universe at a genuinely interesting moment in its own history to be observing it from. The cosmic web is still largely lit, still visible across billions of light-years to any telescope pointed in the right direction. The largest bound structures, superclusters like our own Laniakea, are close to as large as they will most likely ever get, but they are not yet isolated. Distant galaxies are still visible, their light still crossing the gaps between filaments to reach us. We happen to exist during the portion of the universe's story where both halves of this process, the crowded and the empty, remain simultaneously observable, before the accelerating expansion described in the later chapters of this episode has had time to carry most of that crowded side permanently out of view. That happens to make studying Today's voids, carefully and rigorously, something close to reading the shape of the universe's own future, written directly into its present emptiness. The same statistics that describe how large, how round, and how numerous Today's voids also carry information about how strongly dark energy has been stretching space over the past several billion years, and by extension, how that stretching is likely to continue. In an entirely literal sense, astronomers studying an apparently empty patch of sky are studying the clearest available preview of what the rest of the universe is quietly becoming. Somewhere out past the edge of the local group, right now, a single distant galaxy's light is still crossing the gap toward us, fainter and a little more stretched toward red than it was when it set out. One small thread in a web that is everywhere at once, being gathered slightly tighter in its densest places, and drained slightly emptier in its barest ones. It is not being eaten. It is simply finishing, patiently and without malice. The same story gravity began the moment the universe's very first whisper of unevenness settled into the light we can still, for now, look up and see. Nothing in this story is malicious, and nothing in it is really eating anything. What looks from a distance like a giant empty void devouring the universe is the same physical process that built every galaxy, every star and every planet, simply continuing to run in the places gravity never quite reached. The faint ripples in the universe's oldest light were never even. Some patches always had a little more, some a little less. Gravity spent 13.8 billion years amplifying that difference into a web of filaments and walls, and it emptied the spaces between them just as surely as it filled the spaces within them. Then dark energy, whatever it ultimately turns out to be, took over the second half of the job, stretching those already empty places faster than gravity could ever catch up. We happen to live at an unusually good moment to see the whole picture still lit, the web still visible, the void still surrounded by galaxies whose light still reaches us. Study the shape of that emptiness carefully enough, and you are not looking at a hole in the universe. You are looking at the same force that made the stars, still finishing its oldest and quietest piece of work, and reading, a little way ahead, the shape the rest of the universe's future is already taking.